Okay, let us start by recalling this result which we have already proved in the previous video. Namely, that if we consider an infinite subset X of the set of natural numbers, then there is such a bijection. Of course, we did not just simply prove this, but something more, namely that this function is increasing and is the unique function with that property. But for now, for the things that now we will see, we need only this much. So let us see the immediate consequence of this result, which is Corollary 816. And the statement of this corollary is this: all subsets of the set of natural numbers are at most countable. Are at most countable. And it's not difficult, in fact it's almost immediate to see why that is so. We can in fact write, although there is no formal proof in the text because of its easiness, but we nevertheless write a proof. So let X be a subset of N. We are not saying anything else about X. So this X, unlike this one, is not necessarily infinite. It may be infinite, it may not be infinite. If X is, in fact those are the two cases we have to consider. If X is finite, then it is by definition at most countable. Because every finite set is at most countable. On the other hand, if X is infinite, then by this proposition X, there is a bijection between N and X, that means that X is countable. Then by proposition 815, X is countable and hence also at most countable. So in this case also, that is the thing, that X is at most countable. That's just it. That is the proof. Next, the next few results are not this easy to establish. They also are in one way or another consequences of our proposition 815, but they will need some more effort to establish. And we will not do it here itself because each such proof is an exercise. So when we are going to solve the exercises at the end of this section, there only we are going to deal with them. But right now let's see the statements. So this next one is corollary 817, and it says this: if X is an at most countable set and Y is a subset of S, subset of X, then Y is also at most countable. And its proof of course is this exercise. Okay, so the proof of this one is in fact not an exercise, but we can do it here itself, and in the text itself it's there. So the proof goes like this: if X is finite, then so is Y, because Y is a subset of X. So every subset of a finite set is itself finite. This is something we already proved when we dealt with finite sets, and specifically here by this result, proposition 3614. Part C of this proposition. It is that proposition, you can remember if you try, which has many parts, where we have all the properties of finite sets. It's that one. So because Y now is finite, it is again by definition at most countable. Then so is Y. Hence Y is at most countable. Now let X be infinite. Now see, it's already given that X is at most countable. Now if X in that case also is infinite, then it is just simply countable, because it cannot be finite. So by definition it should be countable. Then X is countable, i.e. there exists a bijection f from X onto N. Note carefully that the existence of this bijection is in fact not coming from proposition 815. It is coming from the definition of countability itself. A set is countable, that statement just simply means this, that there is at least one such bijection between X and N, which you according to your convenience can choose to be a function from N to X or from X to N. It actually does not matter, since See, for example, here we have chosen it from x to n because we will see we need this. But if for some reason you also need a bijection from n to x, you can just consider the inverse of f. It exists because f is a bijection and it is itself also a bijection. Okay, so you can choose according to your convenience which one of these two functions you need. Now, the restriction f from y to n of our original function f to the subset y, which is a subset of x. Let's just mention that also explicitly. To the subset y is injective or one-to-one. And this is something that we have already seen in when we were studying functions. There we saw that if we consider a one-to-one function, an injective function, on some set as its domain, then if you restrict the function to a subset, consider that itself as the domain, keeping intact the formula for the rule for the function, then the restriction also becomes injective. And this is in fact something which you can almost immediately see why that is so. Okay, I am not going to go, not going to say anything further on this. We already know this. So, the function f from y to f, okay. Now, this is injective. The original function is surjective, this restriction is injective, simply because the original function is injective. But the original function is, I say surjective, no? So I actually wanted to say bijective. What I am trying to say here is that this original f is bijective, and that's why it is also injective, and that is why this restriction is injective. But the restriction itself may not be bijective, that is, it may not additionally be onto. The image of y under f inside n may not be the entirety of n, it may only be a proper subset. But if we further modify this restriction to this, say we now only consider f to be a function from y to f of y, instead of considering the entire n, I am just considering actually the image itself, then this additionally becomes onto as well. In case this restriction itself is onto, this f of y in fact is nothing but n itself. So you don't have to worry about whether this is equal to n or a proper subset of n. The fact now is that this function is again a bijection. So the function is both one-to-one, that means injective, and onto, that is surjective, or in other words, this is a bijection. Now, whenever we have a bijection between two sets, we say that they have the same cardinality, which just simply means this. Okay, whenever we say that two sets have the same cardinality, that just simply means that there is a bijection between them. Hence, y and f of y have the same cardinality. But now notice that because f of y is a subset of the set of natural numbers, it is at most countable by the previous corollary. Or in fact, is it the previous? Yes, it is the previous corollary that all subsets of the set of natural numbers are at most countable. Since, so because f of y now becomes at most countable and it has the same cardinality as y, so y would also be at most countable. Since f of y is a subset of the set of natural numbers, it is at most countable by corollary 816. So y is at most countable, and this is what we wanted to prove. Now after this we have some other results whose proofs are left to the exercises. So let's look at this next one. This is proposition 818. And the statement goes like this: let y be a set and if from y to n be a bijection. Is it a bijection? No, n to y. Sorry, I looked at something else. Be a function. Nothing else is said about this function. It may or may not be one-to-one. It may or may not be onto. Anything can happen. It's just simply a function whose domain is n and range is y. Then the image of n under f is at most countable. And for its proof, we will see exercise 814. You can in fact see from this statement that y really does not play any role other than being the range of this function. The real part is this n and its own countability, which makes the image f of n either finite or countable. Okay, whenever it is infinite, it will be countable, and whenever it is finite, of course, it will be finite. And it will all depend on the function f itself, how the function is mapping the natural numbers. Note one more thing, that y in fact need not be a subset of n also. Y can be any set. The elements in y need not even be numbers, they can be other objects also, but it does not matter. Whatever function f you have whose domain is the set of natural numbers, range is any set, the image will always be at most countable. So we will prove this in exercise 814. Next we have a corollary to this proposition. Corollary 819, and it says this: let x be, in fact this in a sense generalizes this proposition, although it's a corollary and in its proof this proposition is needed, but still this statement that now we are going to write, it's more general than the previous one. Let x be a countable set and let, again a function is given, f from x to y be a function. Here also, just like this proposition, y in fact is just simply there to have the full function, that's all. Y does not play any other role, and the role that n plays here now is being played by x, but you see a slight generality. I mean, apart from the fact that of course x is any set in place of n, n is a fixed set, apart from that the further generality is that now x is allowed to be at most, is it at most countable or just simply countable? Oh, it's given to be countable, I was thinking at most countable. Fine. So in place of n we have just we now have x, so which is any countable set. Now I was thinking at most countable. If we take x to be at most countable, then what is the conclusion of this? Then f of x is at most countable. Yeah, in that case also it would work. Okay, let me just first complete the sentence and then we can see what all these things are. Then this is at most countable, and its proof also is one of the exercises. For its proof we have to see exercise 815. So now n has been replaced with a general countable set x. What I was thinking is that x is not countable but rather at most countable, but you can in fact write that also. In place of this statement, if you just slightly modify it to consider an at most countable set x, then also this would work. Do you see why? It is because we have a countable x here. At most countable means what? That sometimes x may be finite also. If x is finite, then of course f of x, the image must be finite, and this is in fact itself a property that we saw back when we studied finite sets. And so f of x in that case becomes finite and hence by definition at most countable. And on the other hand, if x is infinite, then it is countable. So by this corollary, again f of x is at most countable. So if you want, you can write at most countable here. That is not going to make much difference, but it can be done. So this is this. Next, the next one is a proposition. and this is a very important one. Let x and y be countable sets. Then their union is also a countable set, and its proof also is one exercise. And it's going to be exercise 8.1, that means the 7th one. And finally, let's see one more result, which we are however going to prove here because it's there in the text also. The set Z of the integers is countable. Recall that towards the beginning of this section, we mentioned that the fact that countable sets, roughly speaking, their elements can be arranged in a sequence, and that sequence can be, the terms of such a sequence can be labeled by the natural numbers. So there we mentioned the fact that the set of natural numbers, the set of positive even natural numbers, all of these, in that sense, we can almost immediately understand why they are countable. In fact, the set of all you can in fact find many such sets. For example, the set of all positive odd natural numbers are countable because 1, 3, 5, 7, that way you can arrange the elements. But there we also mentioned that as we go to the more and more complicated sets of numbers, say after that comes the set of integers, and then the set of rational numbers, the set of real numbers. In fact, if one goes further, the set of complex numbers. Are they countable or not? We do not really find this fact that the elements of a countable set can be arranged in a sequence quite useful to discern whether these sets are countable or not. But there we also mentioned that the integers whose elements can be somehow arranged like this as a doubly infinite sequence. We find it somewhat difficult to understand why this should be countable or should not be countable, because how would you arrange the elements of this set in that way so that you can label all its terms by natural numbers? But now with the help of this proposition we can do that. So let's see how this can be proved. We know that the set of integers is the union of the set of natural numbers and this set, where I'm just simply making this up, okay, this notation, it's not any standard notation. This is the set of all negative integers, that is minus n, where n is a natural number. Consider the function. In fact, you already understand what we are going to write next. We are now going to show that this n minus is a countable set, and from this set builder notation of this set, this expression, you can understand what function I am talking about. We are going to map every n onto minus n. Where f of n is defined to be equal to minus n. We can see that f is a bijection. We can see means, please you go through the actual procedure of verifying that this is a bijection. You first show that this function is 1 to 1 and then you show that it is onto. That's just it. It's very easy, but it needs to be done nevertheless. This is a bijection. Hence, this is countable. But we already know that n itself is countable. So by the previous proposition, their union, that is the set of integers, is countable. So by proposition 8, 1, 10, because this is 8, 1, 11. The set of integers is countable. So by forming the set of integers from the set of natural numbers, we do not get any new kind of infinite set. We get that same cardinality, that of the set of natural numbers, the smallest infinity. So this is where the proof stops. And let me just stop the video here itself. We are going to continue next with the other things. That is, in this somewhat indirect way, we have now been able to show, with the help of those previous results, that the set of integers is countable. The next natural thing to do is to show that the set of rational numbers is also countable, which however would need some more tools. For that, we would need to somehow link countability and Cartesian products. Once we do that, then we can prove. Somewhat going along the same type of arguments, that the set of rational numbers is also countable. So even in spite of the fact that the rational numbers are quite dense, in the sense that between any two real numbers you can find a rational number, still they turn out to give you only this kind of discrete infinity, a set whose infinitude is not in a sense more than the infinitude of the set of natural numbers. But for real numbers, that's not the case. The infinity that the set of real numbers represents is more than this lower infinity. And in fact, it's a very interesting question in mathematical logic or mathematics in general, is there any infinity that lies strictly between that of the natural numbers and that of the real numbers? The guess is no. In fact, and that is continuum hypothesis. It has been proved that the continuum hypothesis is independent of the axioms of Zermelo-Fraenkel choice set theory. That is, using the axioms that we have so far seen, or some other ones that we are going to see in this chapter itself, you cannot prove or disprove the continuum hypothesis. It lies outside the universe that is tractable by the ZFC. Okay, so with that, anyway, I end things here itself. So the next video is on Tuesday. So on Tuesday, let us do number theory. Okay, let's change the sequence a little bit, and then of course we are going to go back to field theory, vector spaces, and all those things. So see you on Tuesday with Barton's number theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.